Thanks. Yeah, so let me just remind you very briefly what we saw yesterday. So I tried to give you some kind of feel for what a gauge theory is. And so the important thing in a gauge theory, the important ingredients is there's this local symmetry group, which usually is called the structure group here also, which I'm always going to write capital G. But the point of gauge theories is that they are invariant not just globally under G, but also under local actions of G. Okay, and so local actions, that's called the gauge group. And so the gauge group, which I'm going to denote by curly G, consists of functions, say little g, that go from whatever your space or space-time is into the structure group G. Okay. And that structure group G is always going to be a compact Lie group with Lie algebra frac G. And then what we have in a gauge theory is we always have a connection, and the connection, which I'm going to denote by A, we can interpret it as a Lie algebra valued one form. And what it does is it really tells you how a state transforms when you transport it from one location to another. Okay. And the way it transforms, so we've seen in the discrete case, your space would be a graph. And so you think of the space-time points as being the vertices of the graph, and you have edges along which you can move. And the analog of the connection would be just an element of G attached to each edge. Okay? And the way we relate the two is we think of somehow continuum space-time as just being some kind of limit of a grid where you just have nearest neighbor connections. And you think of the element G that's attached to a nearest neighbor edge as being essentially just e to the epsilon ai at the location of, say, the midpoint of the edge. Okay? And so then when you have such a connection, so in the discrete case, it's clear that if you follow a path, so if you just, instead of just traversing one edge, you go from one point in the graph to another point by traversing, you know, any number of edges, then there's naturally an element of the structure group that's associated to this. So if you have a state in one location, you transport it to a different location by traversing a number of edges, then of course the effect is that given by simply, you know, applying the different elements of G one after the other, right? So you just first move from here to here, then to here, then to here, and so on. And every time you apply the element of G corresponding to the edges that you traverse. So in the continuum case, that operation would correspond to essentially solving an ODE, right? Because if you think of, say, I have a path like that, I'm going to call that, say, A. And so a path is just, say, a smooth function from 0, 1 into your configuration space. Then say here is A of 0, here is A of 1. And I'm always going to think of it as, well, so you can kind of subdivide 0, 1 into, you know, lots of little segments. So say here you have an x1, x2, x3, or, well, maybe I should have called it t1 also, doesn't matter, etc. And then what's called the holonomy of A along the path little a. If you want, I can think of it as being the limit as this partition sort of goes to 0 of, you know, gamma, say, x0, x1 times gamma x1, x2 times and so on times gamma, say, xn minus 1, xn, right? But now each of these gammas is really some e to the epsilon, where epsilon would be sort of the distance between successive points, right? It would be e to the epsilon a, well, actually I can write it as a of x. Let me actually write it like this, right? So it's a of x at dx, right? So this epsilon here is actually really a dx. It's some little vector that tells you in which direction you move. And the a is a one form, right? And so if I feed it the vector dx, that gives me an element of the Lie algebra, a very small element of the Lie algebra, and then I exponentiate it, I get an element of the group, and I multiply all of these group elements. And if I send sort of the length of dx to 0, and I sort of refine my partition, then, you know, at least if a is a, you know, reasonably smooth function, say continuous function is good enough, then that will converge to a limit, and that's called the holonomy of the connection A along the path little a, and that is really just the group element that allows you to transport a state at the target here into the point at 0. Okay, so the transport here goes kind of backwards like that. Right, that's because of the order of multiplication. Because you always first apply that guy and so on. And that's the guy that you apply last. This you can write, of course, this limit here, you can just write it as an ODE. Right, so you can think of, you know, by how much does this thing change every time I add a little piece? So it changes by some kind of little infinitesimal amount. If you think of what the ODE is, so if I write, say, ft to be the holonomy of A along, say, AT, where AT is now the path which I just stop at time t, right? So the AT would just go up to here, say time t. And this guy would be my AT. So, oh, and by the way, so you see that this is parametrization invariant clearly, right? So somehow the fact that A goes from 0, 1 to RD rather than 0t or whatever, it doesn't make any difference, right? This is clearly parametrization invariant. And so if you look at the holonomy sort of along a path A up to some time t, and then you vary t, what you see from this expression here, if you just, you know, if you sit down for a couple minutes and you just figure out what it means, it really means that f solves the differential equation dft is equal to ft times a of at dat. Okay, so the way you should interpret this is that you can think of the A as being an R2 valued function, right? It's a or Rn, say Rd valued function. Okay, so it's a function with values in, well, linear maps from Rd into your Lie algebra. Dat, you think of it as just being a dot, right? So I can divide by dt on both sides. And so this is just a dot. which is an element of RD. So this is in RD. You apply A to it, you get an element in the Lie algebra. And this guy is a guy in the Lie group. The Lie algebra is in the tangent space of the Lie group at the origin, but multiplying on the left with an element of the group moves it into the tangent space of the Lie group at that element, and therefore everything makes sense, right? So this right-hand side does indeed belong, so this guy belongs to the Lie group G, and the right-hand side here at time t does indeed belong to the tangent space of the Lie group G at the point f.
Martin?
Yes.
You are frozen, at least on my machine.
Oh, sorry.
It was a really short period of time, so I think
weird.
it's okay.
Oh, yeah, it somehow switched from one of the Wi-Fi networks to the other one. I don't know why, but now it seems okay. Now do you hear me again?
Yeah.
Yes, yes, yes.
Okay. Yeah, somehow it looks like it lost the Wi-Fi connection and just reconnected. Okay. Yeah, so I don't know where you lost me, but so basically the point, what I was saying is that this holonomy here, it's not very difficult to see that if you take that limit and the A is sufficiently smooth, then that limit is just a solution to this ODE. Right? And this ODE is just an ODE on the Lie group G. So now, okay, so now if you have a gauge theory, you have the structure group, you have the gauge group, you have this connection. And the idea is that physical observables of the theory have to be functions of your data, which at this point is just the connection, which are invariant under the action of the gauge group, right? So we've seen yesterday that the gauge group has a natural action on the space of connections, which was just basically conjugation plus an extra term. And now physical quantities have to be, right? The idea is that the gauge group is a symmetry group for your theory. So no experiment should be affected by acting with the gauge group. The outcome of an experiment should never be affected by acting on your state with the gauge group. And therefore all physical observables, they have to be functions, if you want, of your connection that are independent of the action of the gauge group, right? That are invariant under the action of the gauge group. And there's one very natural class of such observables, which are called Wilson loops. And they are given by essentially traces of holonomies along closed curves. Okay. So the point, so one thing that we've already seen yesterday, I think, was that if you act with the gauge group, if you look at the holonomy along a curve, and then you act with the gauge group on A, then that's the same as just taking the holonomy for the original connection and then multiply on the left by G of A naught and on the right by G of A1 inverse. Okay, so the way that the gauge group acts on holonomies is basically by, multiplying. So a holonomy is along a curve, there's a starting point, there's an end point, and essentially multiplies by the value of your the value of G at the start point, and then on the right by the inverse of the value of G at the end point. Okay? And now if the start point and the end point are the same, then of course that guy is the same as that guy here. And now of course that's still not invariant, right? Because conjugation is not invariant. But if you apply any function to it, which only depends on the conjugation class, then yes, that's correct. Yes, so the G, so that was what we saw yesterday, the way that the gauge group acts on the connection was this action here. That's right. So it's conjugation minus this dg times G inverse. And so you see here, if you apply to this any function, if you take a closed loop so that this guy is the same, and you apply to this any function which is which only depends on the conjugacy class of an element of G, well then of course you get something which is invariant under the action of the gauge group, right? Because this is just conjugation by some element, and so obviously it doesn't change the conjugacy class. And well, a natural class of functions, and actually they're pretty much all the functions that only depend on conjugacy classes, are traces. Okay, so you just take a representation, say rho of G, and then consider, do we have a name for that? I don't know. Let me, what? W rho, so W for Wilson, rho is the representation, A is your connection, little a is a loop. Okay, so now this guy is a loop, not just a path. So the endpoint is the same as the starting point. And then this, by definition, is the trace of rho of the holonomy of A along A. Okay, and by what I just said, clearly W rho of G acting on A is actually equal to W rho of A. Okay, so now we have a class of observables that allow you, well, that are invariant under the action of the gauge group. Okay, it turns out that, so these observables are, in some sense, pretty much exhaustive. So in the following sense, just that, well, so since we have this action of the gauge group on this space of connections, and we want all of our physics to be invariant under this action of the gauge group. And so a natural thing to introduce is a space of gauge orbits, right? So an orbit would simply be an equivalence class, if you want, of connections, where you postulate that two connections are equivalent if you can transform one into the other by the action of some element of the gauge group. Okay, so gauge orbits. We say that A is equivalent to A bar if there exists an element of the gauge group such that A bar is equal to G acting on A. Okay. And so if you want your actual state space, so the physical state space, then you should think of it as being connections modulo G, or modulo that equivalence relation. Okay? So you consider two connections basically as equal if they only differ by an element of the gauge group, and that would be your physical space, right? So it's in the same way as for electromagnetics. if you describe your electromagnetic field by a vector potential and the potential, then, well, for example, the vector potential we've seen, you can add to it the gradient of anything you want, and you still get the same magnetic field. And so, you know, so in that case, of course, what you do is you just describe, you know, you just take the magnetic field as your state variables. But of course, if you go back and you take the vector potential, then the natural thing to do is to say, well, I actually quotient my space of vector potentials by the equivalence relation of saying that two vector potentials are equivalent if they only differ by a gradient. Okay. But then that's, of course, the same in that case as just looking at the magnetic field. Here, things are nonlinear, so you don't have such a nice description of what this quotient space looks like. Right? So there's no, actually, I think there are even theorems to the effect of saying that you cannot actually have like a global chart on that space of gauge orbits, right? Like you would have in the flat case in the electromagnetic situation, in the abelian case. Okay, so now your gauge orbits, there's actually a little, so let me just show you a little proposition which allows us to sort of characterize, if you want, these gauge orbits. And that says that, so A and A bar are equivalent if and only if you can find a point in RD and an element of your structure group such that if you take one of these loops, the holonomy of A bar along A, that's equal to G naught holonomy of A along A, G naught inverse for all loops A that are based at X. Okay, so based at X just means that it starts at X and it ends at X. Okay. So this, I mean, you should sort of think of this as basically telling you that, you know, these Wilson loop observables kind of determine the equivalence class. Right? So we've seen that they are invariant under the gauge group. So clearly, if two things are equivalent, all the Wilson loop observables are the same. And this is some sort of a partial converse. It's not exactly a converse, but morally, it's some kind of a converse to this. Okay, so you would like to have a cleaner statement would be to say that if all Wilson loop observables are the same, then the two connections are equivalent. This is a slightly weaker claim, which is much easier to prove. So in one direction, this is obvious, right? So we've already seen that, well, if A is equivalent to A bar, then wait a second, this is not. Is this the correct statement? Or do I want the G naught to allow to depend on A bar? No, I don't think I allow the G naught to depend. Oh, I allow the, oh, okay, so the G naught could depend on, it's not allowed to depend on A, but I think it's allowed to depend on A bar. Oh yeah, but that, right, no, the statement is correct. Okay, yeah. So the G naught, okay, so I have two connections, A and A bar. I want to check if they're the same. And then the claim is they're the same if and only if you can find the point X and the element G naught so that this is the same for all loops A. But the G naught, of course, could depend on the pair A and A bar. Okay? In principle, the point X as well. But of course, in particular, the proposition proves that if you can find one x with that property, then every x has that property, actually. Right, so one direction is obvious, right? Because if A and A bar are equivalent, that means that I can write A bar as G acting on A, and then the holonomy of A bar along the loop little a is just G at the point A of 0, which is x, conjugating the holonomy of A along the loop, right? That's what we've just seen before. So in that case, the G0 is just G of x. And now what we want is go the other way around, right? So the claim is that this is if and only if. So if two connections are such that all these holonomies are the same, modulo conjugating by some fixed element G0, then they actually have to be equivalent. And so all I have to do, so what I have to do for this is I have to essentially exhibit an element of the gauge group which transforms A into A bar, right? So I have to find a G so that A bar is G acting on A. And of course, in a way, there's not much choice for what the G should be, right? Because we've seen that if you, so if you take a path, say AXY, that connects X to Y, right? So this notation just means that AXY is a path in RD with AXY of 0 is X and AXY of 1 is Y. So it goes from X to Y. So if I have a path AXY that goes from X to Y, and A bar is equal to G acting on A, then the holonomy of A bar along AXY, that would just be G of X, holonomy of A along AXY times G of Y inverse, right? And therefore, well, I can extract from this G of Y. All right, so therefore the G of Y is just, well, I move that stuff to the left and I take the inverse, right? So I get the holonomy of A bar along AXY inverse times G of X, but the G of X is really our G0, right? We've already seen. And then holonomy of A along AXY, right? So if there is a G so that A bar is equal to G acting on A, then it has to be that G, right? So I have a candidate, and then all I have to do is to check that this G actually does the trick. So the first thing that you would want to check is that this actually, right? So I want just a function of Y, and here I've extracted that function of Y by taking an arbitrary path that connects X to Y. Of course, the first thing you would want to check is that this doesn't depend on which path you choose, right? So that if here you've chosen some different path going from X to Y, and you defined the G of Y using that different path, then you'd want to know that you actually get the same answer. But that's quite easy to check, because say I define G bar of Y in the same way, but replacing A by A bar, where A bar is just a different path that goes from X to Y, okay? Then I can just check what is, say, G of Y times G bar of Y inverse, right? So this would just be, well, the thing that I've here, right? Holonomy of A bar AXY inverse, G0 holonomy of AXY. But then what do I get? So then I have the G bar inverse. So G bar inverse, well, it's sort of the same thing, but I just swap the order of the factors around. So now I have a holonomy of A along A bar xy inverse. Then I have a G naught inverse. And then I have the holonomy of A bar along A bar xy. Right? But now the claim is that this all collapses because so this here, right, is really just the holonomy along a loop, right? Because these things compose. So the holonomy along the concatenation of two paths is just the product of the holonomies. And the inverse of the holonomy is just the holonomy along the same path, but following backwards, right? And so this here just means I first go, instead of going from y to x, I follow it backwards. So I go from x to y, and then I go back from y to x, right? So this is the same as just the holonomy along a loop that goes from x to y, which is the loop that I get by just following first the A bar guy backwards and then the A guy, okay? But then the holonomy of A along a loop conjugated with G naught, that is just the holonomy of, by assumption, that's just the holonomy of A bar along that loop, right? And so this whole thing, I can just write it as the holonomy of A bar along this loop, right? But then that means that I can just delete the G's and replace the A's here by A bars. So these A's by A bars. And then that guy cancels out with that guy cancels out with that guy, and I just get the identity, right? So from this simple calculation, I see that this is well defined. So it doesn't actually depend on which path I use to go from x to y. And then you can do a similar sort of calculation. Maybe I don't want to do the calculation. Well, it's just based on, you want to sort of extract the A out of these holonomies, right? And then to compare the A to the A bar, right? So now we have a candidate for G. We want to check that this identity is really satisfied. And so I want to somehow extract, right? So the assumption is this identity here. So we have information about the holonomies. We want to extract information about the connection. So we want to have some kind of expression that allows you to extract information about the holonomy, about the connection from the information about the holonomy. But that's sort of easy, we know that the holonomy is kind of, it solves that differential equation. So that was actually by definition. But now out of this, here I can just multiply both sides by F inverse, right? So this differential equation here is equivalent, of course, to just writing A of AT dAT is equal to FT inverse dFT, right? So I just multiply both sides by F inverse. But now on the left, we have exactly the sort of thing we want, right? So this is really just the holonomy at a point. And this is just some, infinitesimal change. So we can extract A from just the holonomies. So we can write, say, A of y dy as being the holonomy of A along AXY inverse, and then the differential in y of the holonomy of A along AXY, right? So this is really just another way of writing the same thing. So we have this identity here, and then of course the same identity for the a bar, right? A bar dy equal to, well, same thing with just a's replaced by a bars. And then all we want to do is we want to check that if we take the conjugation, if we take g of y times a of y dy, g of y inverse minus, this was supposed to be an inverse, minus dg of y, g of y inverse, then this should be equal to a bar of y dy. Right, and now this is again just a sort of 2 or 3 line calculation where we simply stick in here, right? So this here, we stick in this expression here. We take the definitions for the g's, which we had here, and then multiply the whole thing out, use that identity, and lo and behold, you have this expression popping out, okay? So at this point, this is just automatic, right? So it's a somewhat boring calculation you can do, so I'm not going to do the details.
So Peter had a
yes.
question.
Yes, but the stronger claim is also true for general. Yeah, so I'm actually not completely sure. So I was trying to check the last couple of days if that stronger claim is true, and I haven't actually quite found a reference. So I tried to prove it, I didn't succeed. So I'm not quite sure whether the stronger claim is true. My suspicion is that it is, so at least I'm pretty sure that it is for the sort of standard Lie group. So if you just take SUN also, then I'm pretty sure the stronger claim is true. If you take some of the more exotic ones, I wouldn't swear it, but probably it's still true. Right, so the problem is so the stronger claim is not so obvious because if you know the Wilson loops, then, so one thing that you can extract is that you know the conjugacy class of every holonomy, right? But just knowing the conjugacy class of every holonomy doesn't guarantee you that you can find one G0 here that works for every loop. Right? So in general, all that tells you is that you can find a G0 so that this is true, but your G0 might actually depend on A. Okay, so if you only know the Wilson loop observables, then a priori G0 might actually depend on A. And then you would have to somehow find an argument that tells you that if this is true with a G0 that actually depends on A, then it actually has to be true also for a universal G0 which doesn't depend on A. And so there is a whole literature about questions along the lines, you know, if you have a group morphism, if you have two group morphisms and you know that they give you the same conjugacy class, then are they conjugate by one element rather than just locally conjugate for every argument? And that seems to somehow really depend on the structure of the target Lie group. So it's true for some Lie group and it's false for other Lie groups. Here, what is the point? Oh, the point X, you mean?
No, yeah, I was saying what was the general, yeah, I didn't understand what was the point of the discussion before. But
oh, the question is, right, so what I mentioned at the beginning is that this is a partial converse to the statement that Wilson loop observables determine the gauge orbit.
Yeah.
Right? And so it's not quite that statement, because if you knew the Wilson loop observables, then you would know the conjugacy class of these guys. And that would be a statement of the same type but with the G naught allowing to depend on A. Right? And it's not completely obvious that if you know this with a G naught that depends on A in general, that then it actually implies that A and A bar are in the same gauge orbit.
Yeah, I see. But then, yeah, but then maybe it should also depend on the space, no, you're looking at, because if you have known, if, for example, if you are on a torus.
Because you could have loops that sort of wrap around the torus.
This even for abelian gauge theory, no, would give you problems somehow. I think, or not. That is.
I'm not sure that gives you problems because the problem is already sort of local. But yeah, maybe.
Yeah. Of course, you have the local problem, but you have also to make assumption on the space, no? Otherwise, will not even. I mean, what you're saying that you have a G0 will depend only, which does not depend on the loop. Even if you manage to establish it locally, you will have problem. I think.
Yeah, you might be right. So you're saying that, right. So you might be able to show that the G0 doesn't depend on the homotopy class of the loop. But then
Yeah, I'm saying that, right. Yeah, for the strongest statement, you have to use some homotopy argument, otherwise it should be fast.
Yeah.
It's not just so requires some topology maybe. Not only like.
Yeah. Anyway, I make no claim about the strongest statement, and just because I don't know whether the strongest statement is true or not. It may be true, but I don't know. Okay. So maybe that's actually a good place for the break, since right. So we're supposed to have a coffee break right now, right?
That's right.
Okay.
We'll come back in 15 minutes. Questions. We'll maybe give 1 or 2 minutes to see if there are questions. Or maybe everyone ran for coffee.
Maybe just in the same line of thought, just as before. But so I got the point that just for like a single group, the fact that all the characters on all irreducible representations, they uniquely determine the conjugacy class. This is true for a group per se. And the problem is just to establish that this G0 is like loop is invariant, is the same, or.
Okay, so the fact that all characters uniquely determine the conjugacy class is certainly true for compact topological groups, right? Because it uses the fact that you have a Haar measure. So I think if you don't have the Haar measure, you might be in trouble. At least for compact Lie groups, it's definitely true, and it's more general. So for example, it's true for finite groups, and it's true for arbitrary compact groups.
Okay, so the problem here is really in showing that this G0 is independent of the A.
Yeah.
Okay. But shouldn't it always be homotopy invariant?
Sorry, say again. Right. Yeah. So, yeah, you would think so, but it's not. I mean, if you just start from that basic relation. So again, as I was saying, so I make no claim in either direction about whether this is true or not, and it may well be that it's known and it's just not known to me, right? So I don't make a claim about things being known or unknown. It's just unknown to me. And yeah, so even within the same homotopy class, right? It doesn't seem to be obvious to show that, you know, if you know that such a guy exists a priori dependent on the loop, it doesn't seem to be, even if you do a small deformation of the loop, it's not obvious that this stays rigid.
Okay.
I mean, if you just write down what it means, it sort of becomes something messy. So.
Martin, can I make a comment? Yeah, I'm always very puzzled of all this generality, because essentially already SU2 is so difficult that that it's enough. I mean, now we are talking about general groups, but already, I mean, all the problem, you have all the problems already with SU2. So you could do all the theory for SU2 would be already very interesting. Also because the physical application are like SU2 and SU3.
Yeah, that's true. On the other hand, okay, that's something I wanted to comment on just after the break, but I can just as well comment on now. If you do the theory for SUN, then it seems you get nice limits as n goes to infinity.
Yeah, sure. That's interesting. Yeah, but I was meaning you don't need more fancy groups, you know?
Right, yeah, so that's right. So people don't really care about gauge theories for, you know, whatever, the exceptional Lie groups of dimension, I don't know what. Yeah, I agree. But I think so at least the statements that I saw from this, you know, local equivalence implying global equivalence,
yeah.
That already made differences between, I don't know, I mean, it somehow wasn't the same for the spin groups as for some of the, I don't remember, it already made differences for some of the standard Lie groups. So it wasn't just about, you know, crazy ones.
I see. Can you give a reference for like this kind of representation theory? I don't know. Do you have any?
Yeah, well, I can send you a link. Yeah, I mean, I found a bunch of papers. So there's some guy was called, what was his name? Larson, I think.
Martin, why don't you just give it to us and we put it on the webpage later? It doesn't have to be live now.
I mean, this is sort of super specialized and doesn't have much to do with gauge theory, actually, but okay.
I think Harpreet had a question.
Yeah, so are there other observables people are interested in additional to Wilson loop observables? I think that, I mean, that's really the standard observable. Okay, so one thing which is nice about Wilson loops is that they're also local observables, right? I mean, in the sense that they only depend on the connection on that loop and not on some sort of global features, if you want. So I think that's one reason why people like them. And then, you know, as far as I can tell, it's very likely that they do actually determine the gauge orbit. So in that sense, if that's true, then in some sense, there aren't any other observables, right? You can sort of construct, you should be able to construct every other observable. So that's just some kind of limit of complicated functions of the Wilson loop observables.
Okay, so if there,
yeah, I have a comment. Actually, one could think things differently. No, I mean, in the sense that the only observable thing is the Wilson loop. Somehow, it's not the. If you think about the physical applications, somehow.
Yeah. So what you're saying is you could have just defined your state space as being the connections quotient. Instead of quotienting the connections by the gauge group, I could have sort of I could have taken as my equivalence relation just that two connections are the same if and only if all the Wilson loop observers agree.
Yeah, something like this. Because somehow, yeah, I was reading even in Seiler book, so I think this what is gauge theory is not so clear from the point of view what you need in applications. Of course, you can introduce the connection and all these things, but at the end of the day, you don't measure any of these things. Okay, you don't measure the connection. You measure only some Wilson loops or something related to Wilson loops, some gauge invariant observables. So, okay, let me say differently. Okay, the only thing you can measure are gauge invariant observables. So
sure,
not surely the connection. It's somehow an artifact of our way of making sense of this structure, as far as I understand. I mean, I don't.
Sure, yeah. No, but the question was whether somehow the Wilson loops are all the gauge invariant observables there is, or if there's more.
But, well, okay. Then if you have matter fields, there is more, but
Sure. But like in pure pure gauge theory.
All right. So if there are no more questions, maybe we'll take a 7-minute break and then reconvene at 11.
Okay, thanks. Can you? Oh yeah, that works. Right. Okay, so now what we've seen yesterday that once you have this, so on that space of connections, you have this Yang-Mills action, right? So let me just remind you. Whoops, that's this Yang-Mills action, which, let me write it, S Yang-Mills of A is just, say, 1/2 norm of f of A square, where this guy is the curvature, and the curvature we've seen is, one can also write it as sort of dA plus 1/2 of A square, and where this norm is sort of an L2 norm in space and kind of a sum of all the components, and in the Lie algebra, you have to pick a norm on the Lie algebra, which is invariant under conjugation. Okay. And so now we want to, what we'd like to do is to sort of, take the usual program in sort of constructive field theory, which is to, well, we'd like to construct, if you want, the Euclidean quantum field theory that's associated to this action. And so in other words, basically what you want to do is to make sense of e to the minus Yang-Mills action of A, and then whatever dA, whatever that means, right? And so the dA here is formally, this is sort of, Lebesgue measure on your space of connections, which of course doesn't really have a meaning. So there are two special cases in which this measure is basically known, right? So there's one special case, which is the case of d = 2. And so there are a number of people associated with this. I think it started with Migdal and Witten, and then there's a number of people who worked on that. More recently, sort of Driver and Thierry Lévy. And in dimension 2, you can basically just guess, in some sense, what the joint laws of all the Wilson loop observables should be under this measure. Actually, what even the joint law of all the holonomies should be under this measure. And therefore, it really determines somehow a measure on gauge orbits. So maybe I can just show you what the measure is in d = 2. So what you do is you draw a graph, but this time it's an actual graph in the way that I'm drawing it on the board, in the sense that it's really a graph embedded in R2 with the edges being really smooth curves in R2. Okay, so it's not a combinatorial graph, it's really an actual graph in R2 with edges that are actually smooth curves, right? So something like this. Planar, okay, so the edges aren't allowed to cross, or if you want to cross them, you have to put a vertex at the point where they cross. And maybe you have to sort of, you can assign an orientation to all of them, right, in some arbitrary way. And so now, since it's in 2 dimensions, we have faces. Right, so we have faces. So here we have a face F1, F2, F3, etc. And we have edges, right, sort of E1, E2, etc., and so on. And now what we want to do is we want to basically, for every edge, we want to assign a holonomy which corresponds to just, you know, that piece of line, right? So every edge here now is one of these curves A that goes from, say, 0, 1 into the plane. And so there would be a holonomy associated to it. And what we want is we want a measure on, we want to describe the joint distribution of all of these holonomies. And here it turns out that that's actually quite simple. So if I write, say, gamma E for the holonomy for edge E, right? And so that would be an element of G. And so I need to give you a probability distribution on G to the power number of edges, right? So for every edge, I want to have a random element of G. And so the way this works is, so mu, say, of Yang-Mills of d gamma is going to be the following. So what you do is you take, well, so as reference measure, you simply take the product of the harm measures, right? So for every edge, you have a sort of d gamma E, and this is really just a harm measure on G. And then you do a product, you take a product over the faces. Okay. And for every face, what you do is you take the heat kernel, so that's the heat kernel on G, at a time which corresponds to the area of the face. Okay, so the time of the heat kernel is the area of the face. And then the argument of the heat kernel, so it's the heat kernel on G starting at the identity. Okay, so at time 0, it would be a delta measure on the identity element on G. And at subsequent times, it's a function on G, and it's a function on G which actually only depends on the conjugacy class. So it's a class function. And the argument here is simply the product of the gammas that border the face. Okay, so here you take the product of, you know, E, I don't know how to write this, sort of, you know, the edges E that go around the face F, and you take the product of the gammas in the correct order, and maybe with the correct inverses if you're going against the orientation that you've assigned to the edge, right? And that's it. And then you just normalize, right? So you normalize this. And the claim is that this measure here is your Yang-Mills measure. Okay, so this is, now of course I can just define this measure and postulate, but now you want some sort of argument of why, you know, why do I claim that this measure here has anything to do you know, with this formal expression here. Well, so there's two things. So first, of course, this formal expression, you want something which is somehow gauge invariant. And that's true here. Okay, so here I can actually multiply. So if I do sort of apply, if I act with the gauge group on this measure, well, then this guy doesn't change, right? Because the harm measure is invariant under translations. And this guy doesn't change either, because here you would just end up doing a conjugation, and the heat kernel is a class function, and so it only depends on the conjugacy class, and therefore it doesn't get changed if you do, if you apply a conjugation to the argument. Okay, so this is invariant So it has two properties. So the first one is that it is invariant under the action of the gauge group. But then, more importantly, if you think of these loops as being very small, then this measure does really look like that. Because you see, what is the Yang-Mills action? Well, it's this f of a square. But f of a, we've seen, how did we define f of a? We actually defined it as being just, you know, the holonomy around a small loop. We just looked at the holonomy around a very small loop. And then we saw that, well, this is very close to the identity. It's order epsilon square from the identity. And so then we just postulate that this is e to the minus epsilon square times something, and that something, we called it the curvature, right? So the holonomy around a small loop is basically, right? So the holonomy around a small loop is basically, by definition, if everything is smooth, e to the minus area of the loop times the curvature, right? But then that heat kernel here is just, well, the heat kernel P of at a small time, right? So if you have a small area, P epsilon of G is equal to what? Well, so first the heat kernel is concentrated very close to the identity, right? And therefore I can write the argument of the heat kernel. It's natural to actually write it as e to the something, right? E to the, say, h, where h is an element of the Lie group, right? And then for short times, the heat kernel is basically e to the 1/2 1/2t, right? So you would have a whatever epsilon here times norm of h square, right? But now that h, for a very small loop, that h is precisely proportional to the curvature. And so what you see here is that this term is essentially e to the minus area of f times curvature squared. Okay, so there's so the reason why it scales like that, so here I have divided by the area, right? So here I've divided by the area, but then on the other hand, the h itself was supposed to be area times curvature, and so h square is going to be area squared times curvature square. So one factor of the area cancels out, and so you get something which is essentially area times curvature square, right? So at least if the loops were really tiny, then there's a good argument that the heat kernel evaluated at the holonomy around the loop, you know, looks like e to the minus area times the curvature square. And therefore the product of all of these heat kernels, now these are actually just real numbers, right? So now the product of the exponentials is just the exponential of the sum. And so this whole product is essentially, you know, e to the minus the sum over the areas of all the little loops times the curvature square for all of these points. And therefore, if you make the loops very small and you know, take many of them to sort of cover the whole space, then essentially this big product starts to look like the integral, you know, the L2 norm in space of your curvature, okay? And then the other reason, right, so that tells you that at least if these loops were very small, and they kind of cover the whole space, then there's a reasonably good argument that this guy is some sort of approximation of this measure here. And then the final property that makes this measure a really good candidate is that it's consistent under edge removal. Okay, so if I take this measure on a very fine grid, and then I start removing edges to turn it into some kind of coarser graph, okay? And I remove it, right? So there's two ways of removing the edges. So one is simply take that definition of the measure for the new graph. The other one is to simply look at the marginal, right? So I have a measure on many edges, and I can remove edges by simply looking at the marginal of this measure on, you know, the edges that are left. And then maybe, you know, I can also remove vertices if they're in the middle of an edge by, you know, doing the natural thing to say that sort of the holonomy along the whole edge is simply the product of the holonomies along the two constituent pieces. So I can also remove vertices. And the claim is that this measure is consistent under both of these operations, right? So if you just take a very fine grid and then start to coarsen it by simply projection, right? By simply projecting that measure onto the coarser grid, then that's actually, you get the same measure back. So you get that measure for the coarse grid, right? So it's consistent under refinement. And therefore, you know, you could take, at least formally, you can take some sort of an inverse limit, right? And then you kind of think of the Yang-Mills measure as being, right? So since this is consistent for an arbitrary number of edges in your graph, and so it completely determines, if you want, the whole Yang-Mills measure. Okay, but this really works only in 2D, right? So this formula already doesn't only make sense in 2D, right? Because in 3D, if you have a little loop in 3D, there isn't even a natural notion of area to it, associated to it anymore, and so on, right? So this is very much a 2D construction. And the other limit where things are known, which has been studied a lot, is what I already was sort of alluding to in the discussion with Max earlier, which is the n goes to infinity limit. Okay, so if you take as your G the structure group, if you take something like SON with n going to infinity, then you can formally get kind of limits where you know, you describe things using free probability, right? In the same way as you would describe, you know, the large scale limit of random matrices using free probability. So that's the other kind of limit which is known. Okay, so what we want to do is we want to take this expression here, sort of more serious, or if you want, really take it almost like a naive starting point, both in 2 and 3 dimensions. And so the way we want to go about sort of attempting to move towards constructing that measure is by doing what's called stochastic quantization, right? And this really, quantization. And so here the starting point is just the sort of silly observation that say on R capital N, if you look at the SDE dx equal to minus gradient V of x dt plus dw, so that one has invariant measure e to the minus 2 V of x dx. Okay, and so one way of constructing a measure of the type e to the minus some action functional times Lebesgue measure is to just look at the corresponding gradient flow and then hope that the process that you construct in that way has an invariant measure, and then you just define the measure as being the invariant measure for that process. Okay. Now, so first, just one simple remark is that, so here you have a gradient. So of course in Rn, you know, gradient just means, you know, sort of differentiate in all the in all the unit directions. Now, more generally, a gradient requires to have some kind of a scalar product, or at least a metric, right? Because the thing which is intrinsic when you have a function on your state space is the differential, but the differential takes values in the cotangent space. Whereas on the right-hand side of an ODE, you want something that lives in the tangent space. And so you want to have a way of going from the cotangent space down to the tangent space. And so the way to do that is to have a scalar product. Right? So then you have an identification between the dual and the space itself. And so here you need a scalar product or a metric in general to do that. But that's the same for the white noise. Right? So the white noise, your noise has a covariance, and the covariance is a bilinear form on your you know, space Rn or whatever that your equation lives in. And therefore that also determines, well, a norm or a metric. And of course you want these two metrics to be the same. Okay, and the claim is that the invariant measure that you get is that measure here, whatever metric you choose. Okay, so if there's a natural metric on your space, you just take that natural metric. Somehow it's not forced upon you. So in our case, because you would want to take for V the Yang-Mills functional, yeah? And we want to take for X our connection. Right? And so we want to write down some kind of an SPDE for these connections. Right, so formally we would get, so we want to consider dTA is equal to some sort of gradient in the A direction of this Yang-Mills functional, and then plus, you know, some sort of white noise. Now, so first let's try to see what that equation actually looks like a bit more precisely. So if I write, so our Yang-Mills functional, so that was of the form f of a square, well, maybe a half, and f of a is dA plus a half times this sort of wedge product with a commutator in the Lie algebra. And so if I take the differential, so let me write sort of curly d to say like this is not derivative in space, it's derivative in the A direction. Right, so the df of A in the direction, say, h, that would be just, well, the linearization of that thing. So it's dh plus, and here you would just get a h because this is symmetric. Okay, because the wedge product is antisymmetric, but then the Lie bracket is also antisymmetric. And so the combination of the two is actually symmetric. So if you differentiate this quadratic thing, you just, well, plot the direction in which you differentiate into as one of the arguments, and you multiply by 2 because it's quadratic. Right, so that's why the 1/2 drops. And now you see here you can actually recognize the covariant derivative that we've introduced yesterday. So this is actually the covariant derivative of h in the direction A. So what does this tell us about our equation, well, if you want to take, if you have anything of the norm of the form, right? So if you have a function of the form 1/2 f of x squared, where you have some norm here, right? And then you want to take the gradient of this, then what do you get? You get the, well, there's a factor 2, another 2 gets cancelled out with the 1/2. And then what you get is f of x acted upon by the differential of f of x adjoint. Okay, so here, let me just set things up properly. So we have some state space, say V, and then F takes values in some other space, W, and both of these are normed. Right, so that's the situation that we've got, because we have the A is a connection, so it's basically a 1 form, and we have a natural norm there, which is sort of L2 with the L2 norm on 1 forms, and with our adjoint invariant norm on G. And on the other hand, F itself takes values in the space of 2 forms, right? The curvature was a 2 form. And then again, on the space of 2 forms, we also have a natural norm, which is the L2 norm. And that's the norm which appears in our definition of the Yang-Mills functional, right? So the definition of the Yang-Mills functional was just the L2 norm square. So the general situation that we have is that we have some kind of function that goes from a normed space into some other normed space. And our functional that we want to take the gradient of is of the form norm square of this function, right? Where this norm here is the W norm, and the gradient is the gradient with respect to the V norm, right? So gradient always refers to a norm, as we've seen. And now the claim is that, and that is something you can just check, right? So that gradient is equal to this expression here. So remember, f of x here is an element of W. The differential of f of x is a linear map from V to W. And the adjoint of the differential is a linear map, well, in principle from W star to V star, but since these guys are normed, the norm gives you an identification between W star and W and V star and V, right? And so you use that identification to identify this guy with a linear map from W to V. Right, so df at x is a linear map from V to W, and so df of x star, I can identify it with a linear map from W to V, because W is identified with W star, and V is identified with V star via their scalar products, okay? And therefore, at least this expression is of the correct type, right? So the claim is that this guy here is now again a function from V to V, right? So X is in V, and this guy is in W, but then this guy moves it back to V, okay? And so at the end, you get a function in V. And so in our case, if we do that, what do we get? Well, we've seen that our df is actually just the operation of covariant differentiation in the direction A. Okay, that's what our df is. df applied to some element H is just dA. And f is, well, f is just f. So that tells us that we would want to consider the equation dTA is equal to minus the adjoint, the L2 adjoint of the covariant derivative applied to f of a, and then plus psi, and now our psi should be a g-valued space-time white noise, right? Because space-time white noise is the noise that has as its covariance the L2 norm, okay? And that's the norm with respect to which we took the gradient here, okay? Since this is the L2 adjoint, okay? Now, the problem with this equation is that, well, there's a problem, there's a very basic problem here, which is that it's actually not elliptic. Okay, and the reason is that, you know, it's basically of the following form, right? So the form of the equation is something like a dTA is equal to minus d star dA, and then plus additional stuff where you only have at most one derivative, right? So this f of a, remember we've seen, well, f of a is just dA plus something, right? That's here. And then the covariant derivative is d plus something zero order. And so the adjoint is d star plus something zero order. And so the whole thing is of the form minus d star d plus additional stuff. But d star, if this was a function, a scalar function, then that would be good because d star d is just a Laplacian. Right? Problem is that this is a one form. And on one forms, d star d, well, it's a second order differential operator, but it's not elliptic. Okay, so the one that's elliptic is d star d plus dd star. But just d star d by itself is not elliptic. Now, the reason why this is the case is actually sort of directly linked to the gauge invariance. Right, because what gauge invariance tells you is that this function v, which is our Yang-Mills functional, right? This function is invariant under the action of the gauge group. The gauge group is an enormous infinite dimensional group, right? It's the group of all functions of your state space with values into G. So it's invariant under the action of an enormous group. And that means that if you think of that as being some kind of energy landscape, that energy is constant, right, in many directions, right? So there's like these infinitely many directions, which is the directions in which the gauge group acts. And that energy functional has to be constant in all of these directions, right? And so now when you take the gradient flow is going to flow, if you want, sort of in the orthogonal direction to the level sets of your energy functional. And sort of that's what gives you something very degenerate, right? Because you have this, well, if it, in some sense, if it were elliptic, right, that means that you would have some sort of very strong coercivity. So if you want anything that kind of measures roughness would decay very, very fast. Okay. But the point is that your gauge group can actually move you in directions that mess up roughness. Okay. And so that already tells you, if you want, that you cannot preserve ellipticity if you want to also be invariant under the action of the gauge group. Right. So, okay. So this is sort of somewhat heuristic, but just because the gauge group acts sort of independently at every point, it can clearly sort of mess up the roughness of your solution. But then on the other hand, you know that your solution will be invariant under the action of the gauge group, the way we've set it up right now. And that sort of gives you immediately a contradiction with ellipticity. So what does one do? Well, so there's a standard trick, and that trick was originally introduced by the Turk. And that was actually in the context of Ricci flow, where you have a similar problem. And then it was used by Donaldson in the context of Yang-Mills. And the trick is to say, well, at the end of the day, we really only care about our measure not on the space of connections, but on the space of gauge orbits, right? So we really want to build a measure not on the space of connections, but on the space of connections, right? So this measure here should be a measure on the space of connections quotiented by the action of the gauge group, right? Because we want to say if two connections are equivalent under the action of the gauge group, well, then for all practical purposes, they are the same. Right? And that's already what we did here, right? So here you already build only a measure on these kind of holonomy type observables. So you don't actually build a measure here on the space of connections as a sort of field. So in this equation here, in some sense, we don't care about modifying the equation as long as the modification is equivalent to just, you know, acting with some element of the gauge group, right? So morally, what we mean is that, you know, you have these gauge orbits. So say here you have an element A, and then here you would have sort of G acting on A. And now you have your flow that, you know, sort of moves you on here. But now if you add a term which goes in this direction, let's just say, draw it in red, right? So if you add a term to your equation which moves in the red direction, so in the directions which are tangent to the gauge orbit, then as far as physics is concerned, you haven't changed anything, right? So all you do is, you know, infinitesimally, you sort of apply some gauge transformations as time goes by. But then applying gauge transformation shouldn't change anything to the physics, right? And so it doesn't actually change what you care about. And so you can ask yourself now, what sort of terms are you allowed to add here, right? So what's the kind of, what is the tangent space to the space of gauge orbits? Right? And then you would want to add to the right-hand side of your equation some term which at every time t belongs to the tangent space of the gauge orbit at A. Right? So if you, hopefully, so the hope then is that you can do that in such a way that the equation you get in that way is actually elliptic or parabolic. It's a time evolution, so that the right-hand side is elliptic. So now, what does the tangent space look like? It's the tangent space. To the gauge orbits. Look like? Well, what we have to do, if we want to see what the tangent space looks like, is basically, well, we take a curve that stays on that gauge orbit, and we differentiate the curve, and then we see, you know, what the thing we get looks like. Okay, so that's going to tell us what the tangent space looks like. So you look at a curve, t goes to g of t acting on A, right? So you take a curve like this, and then you differentiate this in t, and you see what you get. Right? So if we take the t derivative of g acting on A, well, then that's the t derivative of g AI g inverse minus derivative of g inverse. Now, if you differentiate the, so A is constant. So in the first case, well, if I differentiate the first guy, I just get the derivative of gt here, which I can rewrite as derivative of gt times gt inverse times gt. So then I have again a term of the form gt conjugating AI here. And then when I differentiate this, I get something of the same type, right? I get sort of like minus gt inverse derivative of gt times gt inverse. And so when I combine both of them together, I get a commutator. So I get actually the commutator of dtg times g inverse with add g AI. So that's when I differentiate the first term. And then the second term, I get the t derivative of this term. And it turns out, if you think about it, you can essentially swap the t and the x derivative. So what I want to do is I want to write it as an x derivative of dtg times g inverse. And of course, that's not exactly the same. The first term is the same, right? So when the t hits the first factor, then that's the same as when this derivative hits the first factor here, right? Because the partial derivatives commute. But then, of course, when that derivative hits the second factor, I get something like a space derivative of g times g inverse times time derivative times g inverse. Whereas here, I get something like time derivative g times g inverse times space derivative g times g inverse. And so the mistake that I've made by replacing this by this is again a commutator, and it's the commutator between dig g inverse and dtg g inverse. Okay, but then if you look at this expression, what you see is that now I have all these dtg g inverses everywhere. I see that these two terms together are actually just g acting on A. Right? So while here it comes with a plus, but it's on the other side of the commutator. So maybe I should have written a minus here and swapped the two terms. Right? Then it looks, then you see that here you get the g acting on A commutator with dtg g inverse. And here you get the spatial derivative of dtg g inverse. And if you combine the two, what you recognize is actually just the covariant derivative of dtg g inverse in the direction of gt acting on A. So now this guy was arbitrary, right? Since g here is an arbitrary function with values in the gauge group, right? And this guy here is precisely this guy here. So what we see is that the tangent space of the gauge orbit at some point consists precisely of all the one forms that are obtained as covariant derivatives of a zero form in the direction of the covariant derivative with respect to the connection, which corresponds to the point where I am on the gauge orbit, right? So the tangent space at A consists of everything of the form dA, say H, where H is just a function from my RD into the Lie algebra. Right? So it's a zero form, if you want. Okay. So I can add, so now what this suggests is I can add to the right-hand side of this equation, or rather this equation here, I can add to the right-hand side of this equation anything of the form dA applied to some functional of A. And that's nice because we already have a term d star d, and now we're allowed to add something of the form d applied to something plus low order. And so in this way, by combining the two, we can create something which has a d star d plus a dd star. So we choose if you want h of A to be minus d star A. And so that now we look at the equation dTA is equal to minus dA star f of A minus dA of d star A, and then plus our space-time white noise. And now this equation is parabolic. And at least formally, it's equivalent to the previous equation in the sense that you would have, you know, if you had a notion of solution for both of these equations, then you would have a time-dependent gauge transformation that maps the solution of one to the solution to the other. Now, of course, actually, we don't have any sort of notion of solution for that equation here because it's not parabolic. And so we simply take this as our starting point. Okay. And so now in the, okay, so I think I'm already out of time. Okay, so let me just say what I'm going to do in the last two lectures. So we want basically two things, right? So now this is our sort of object of study, is this equation here. We would like two things. So first, what is a good state space? Right? So a good state space, well, you would want something with some gauge invariant observables, maybe with Wilson loops. Ideally, you would want to have some sort of space of gauge orbits. So you would want to take some space of connections quotiented by the action of the gauge group. But so far, all the reasoning we did was with smooth objects. Okay, and so now they're going to be very much non-smooth, and there it's not clear what you can do. Right? How does one see that the new equation is parabolic? Yeah, because now the dominant bit, right? So this equation now is of the form minus d star dA minus dd star A, and then plus a whole bunch of stuff, plus psi. And this stuff, I don't write it down explicitly, it involves sort of, there's various sort of quadratic and cubic expressions in A and their derivatives, but the point is that it contains at most one derivative, right? So every term in here contains at most one derivative, right? So that guy comes from the fact that the first term in our covariant derivative is a D, and so the adjoint gives you a D star, and in the definition of f of A was dA plus lower order. So that gives you the D star D, whereas here again, well, you have a D star already, and then the first term in the covariant derivative is a D. So that gives you a dd star here. Okay, and this is just the Laplacian on one form. So that makes it parabolic. right? So you want a good state space for this equation. So you want maybe a space of gauge orbits or something like this. And then the other kind of question that you want to ask yourself is, what about gauge invariance? You would sort of, the minimum type of invariance that you would want is the fact that if you start with two initial conditions that live on the same gauge orbit, and then look at the two solutions that you get by sort of solving from these two initial conditions, right? So you have one process starting with some initial condition A0, another one starting with some G0 applied to A0. Then here you get some AT. Well, and then what you would want is that, so at least in law or something, that the solution here is some GT applied to AT. Right? So you would want to have some gauging. That would be a sort of relatively weak form of gauge invariance, right? So you'd want to know that if I start from different points on the same gauge orbit, then as far as the physics is concerned, I can't distinguish them, right? That means that if I look at the solutions at a later time, they must also be comparable by a gauge transformation. Okay, so I want some kind of gauge invariance. But then one question is, how does this play with renormalization, right? So you know that, so this is going to be some sort of horribly singular stochastic PDE. If you want to give a meaning to it, you might have to do some renormalization, but that might mean that you have to sort of add some extra term to the right-hand side. But this whole setup in gauge theory is incredibly rigid, right? So I told you at the beginning that this Yang-Mills functional is pretty much the only thing that you can write down, which is gauge invariant and, you know, has the right scaling properties. So that means that, you know, whatever extra term you add, it's going to break gauge invariance. And so you're not really allowed to add anything. And so the question is, what does that mean for renormalization? Does that mean that you don't need any renormalization? Or what actually happens, right? So that's the, so that's basically the two kind of questions that I want to address in the next two lectures. Okay, so in the next lecture, we're going to talk about mostly about the state space. And then in the last lecture, we're going to talk about gauge invariance and how it links with randomization for that equation. Okay, so that's it for today. Thanks.
All right, everyone. So thanks, Martin, for that lecture. So maybe everyone can unmute and clap. So at this moment, maybe we can take a few questions. Okay. Oh, well, okay, now you can do it. Now you can do it. Okay. Sorry about that. Okay. Yeah, so are there any questions?
Cool. Maybe one small question. Could you also just like fix a gauge? You say I fix a Coulomb gauge for A, and then I look at the equation.
Well, okay. So one thing is that there is no global way of fixing the gauge, right? So so you can sort of locally you can fix the gauge, and then at some point you might hit a singularity of your chart also, and then you might have to move to a different gauge or something. In some sense, you can view this adding this extra term as some sort of dynamical gauge fixing. Okay, so that maybe that's sort of like a good way of interpreting this, right? So it's like a dynamical way of fixing the gauge. Okay. But yeah, I mean, you cannot so the problem with these things is so locally you can fix a gauge, so you can sort of fix Coulomb gauge or something, but none of these ever always makes sense globally on the whole space of gauge orbits, right? So that's actually a theorem, that there's no global way of fixing gauge in general.
Okay, I think Henri has a question.
I think Henri wanted to ask something.
Yes, so in the 2D picture, so you have this nice description of the invariant measure, and I was wondering, would there be correspondingly a nice description of a Markovian evolution? Should have the
Okay, so our conjecture, of course, the natural conjecture is that the evolution that we construct in 2D has an invariant measure, which if you just project onto Wilson loop observables or on these holonomies, coincides with the measure that was defined here, right? So that would be a very natural conjecture. I mean, I have no doubt that this is true. It's not a theorem at the moment, but yeah, I mean, it's almost certainly true. So in that sense, it does give you a Markovian evolution, which has this measure as an invariant measure.
Okay, thank you.
Yeah,
looks like.
Can you hear me? Yeah, okay. So the choice of representation for the Wilson loops, does it matter, and does it appear again?
What do you mean by the choice of representation for the Wilson?
So when you define these Wilson loops, you chose some representation from the structure.
Oh, I see. Oh, yeah. Okay, I see. No, it doesn't matter. I mean, in most cases, people just look at, you know, SON anyway, and then you have there's a canonical representation, which is that you already have matrices, and then you just take the trace of the matrices. But yeah, no, it doesn't matter.
Can I just follow up on Henri's question? So you were in the 2D case, but do you kind of have a good evolution of how this law of these finitely many loops would change over time? Can you describe the Markov dynamics there? Do you have a conjecture there?
No, like having an explicit, no, I don't think
any sort of description.
Right. I don't think that there's a conjecture there.
Okay.
I don't have a conjecture. Well, I haven't really thought about it, but I wouldn't necessarily expect to have something. I mean, it's, you know, it's like, for example, you know, you can say tons of stuff about 2D conformal field theories, right? So you have the scaling limit of Ising model at criticality, and you have all sorts of stuff like that. If you stick dynamics onto the Ising model, you don't even know what's the correct exponent to get a scaling limit, right?
Right.
So just because you know a lot about the measure sort of in the 2D case doesn't necessarily mean that you know a lot about the time evolution.
Okay, thanks.
Yeah, I think there's a raised hand.
For the processes that you made that you wanted to gauge invariance in the last slide, is it too much restriction that the gauge invariance doesn't depend on time?
Yes, that's too much restriction. That's basically what would happen for this equation here, right? So if you had a way of giving a meaning to this equation here, then the same sort of picture like here would be true, but with this guy not depending on time, right? With this guy just being the same as G naught. But, you know, as soon as you add an extra term here, basically, if you want to see what the GT should be, the equation you would want to write down for GT is basically something like time evolution of GT is given by the extra term you've added on the right-hand side. So as soon as you add something, then that tells you that that guy actually moves. how do you define a white noise on the Lie algebra? Oh, you have a, well, the Lie algebra is just a copy of Rn, right? So the only thing that you need to describe is the covariance. But now a covariance is basically the same as giving yourself a norm. And you have a norm on your Lie algebra because there's one norm which is invariant under conjugation. And it's uniquely determined by that, well, modulo scalar multiples, okay? And so then the white noise is just d white noise with covariance given by that conjugation invariant norm.
It looks like
it's not a white noise on the Lie algebra, right? So it's a white noise with values in the Lie algebra. Okay, so it's a white noise on your physical space, which would be R2 or R3, or maybe two-dimensional torus or three-dimensional torus, and with values in the Lie algebra, actually with values in one forms, right? So it's values, so these guys have I's in principle, right? So there's an I here, and there's an I here, and there's an I here, and so there's an I here, right? And so the I is a spatial index, and now for every I, your psi I is a Lie algebra valued space-time white noise. Okay, and the covariance it has on the Lie algebra is given by that ad invariant norm.
It looks like Milton has a question.
Yes, so I want to go back to Henri and Hendrik's discussion, because in 2D, okay, you mentioned that you have consistency, you know, of the Wilson loop. So that's actually a property that you don't have in, like, for example, in the Ising model.
What do you mean? I mean, so here consistency, I mean, you should have consistency, right? I mean, consistency just means that you have a well-defined measure.
Yeah. Right? But I mean, what I meant is that you can, for example, here you can add an edge. That's something that you cannot really do in the Ising model, no?
Yeah, okay, I see what you mean. Yeah, that's right. Yeah, but here it's true. Yeah, so here you have really, in some sense, you have a consistent family of these measures on the, so you can take arbitrary graphs sort of embedded in a smooth way in R2, and then you can modify them in arbitrary ways. And as soon as sort of these modifications are kind of well, so if the modification is sort of a simple one, so where one graph is strictly larger than the other one, then the measure on the smaller graph is always obtained by just projecting the measure on the larger one. So that's why then you have some sort of an inductive limit, if you want.
So that means that maybe you can do the same for dynamics, no?
Right. Maybe. But you know, I mean, the fact that these things are consistent is already, it's sort of non-trivial, right? It's not a completely obvious thing. And then also you see the way that measure is described, it's described really as a measure, right? So you really describe the density with respect to some sort of reference measure. And it looks like some sort of a product measure, but it's really not a product measure at all, because the same guys here appear in more than one face. Right? And so you don't have, for example, you don't have an explicit description in terms of like random variables. Right? It's not like I can say, oh, if you give me whatever white noises or I give me something, then I can construct, if you want, a collection of random variables that has this measure as its law. Right? If you see what I mean. I mean, in the sense that, like, if you want to construct a dynamic, it would be much easier if you had some sort of a description in terms of simpler random variables, right? In terms of taking simple random variables and then transform them in a certain way in order to get that more complicated measure. Because again, you could think of a dynamic on the simple random variables and then just push it forward on a transformation, but you don't have a description like that.
All right, so there's one question from Harpreet in the chat and one question from Trish, but then maybe further questions should go to the Discord afterwards.
So the loops area by volume and faces. No, but you can't. So I think Harpreet, you're thinking about sort of generalizing that to 3D, right? But there's no
explicit.
but it doesn't work, right? Because you would want to how do you associate a holonomy to a face? I mean, yeah, so again, you can go around the face, but then it's sort of, at the end of the day, holonomy is always about one-dimensional parts, right?
So what I was thinking of, to replace somehow the reference measure, index it by the faces, and take kind of the same reference measure. And then just in the formula, replace area by volume and every edge by that face somehow.
Yeah, but that wouldn't be, in some sense, that wouldn't even be an object of the right type. Right? Yeah. Because giving yourself an element of G for every face, it's not, right? So that doesn't really have a meaning in terms of gauge theory, right?
Yeah, so I was just wondering.
And also there's not a natural, right? So the difference is that faces, there's no natural order between faces. So if you have paths, you can concatenate two paths, but it's clear somehow, right? Either the first guy comes before the second guy or the second guy comes before the first guy, and that plays well with the composition operation in a group, right? If you have faces, there are lots of ways of sort of putting faces together, right? So that's not at all, right? So how do you make that consistent with the group operation?
Mm. Okay, I see. Thanks.
Okay, and I guess Trish had a final cultural question.
Yeah, so I don't know if that's exactly what people use, but yes, I do. They do use MCMC to simulate sort of lattice gauge theories. And so I guess it must be some sort of discrete version of this type of dynamic. But I don't know exactly. I mean, I haven't really looked at what type of dynamic they use for their MCMC.
All right. So at this point, we should close. And now you're definitely all able to unmute. So let's give one more round of applause. And I believe that we'll reconvene at 1 for Roland Bauer.